Today we're going to be talking about electron configuration. This is our introduction. So it's really important to understand the forces that are acting on an electron. So remember that with electrical force, because there are two different charges, electrons and protons, there are two different kinds of forces of attraction. Electrons can be attracted to protons, and the protons are in the nucleus. But electrons are repelled by other electrons. So we have force attractive and force repulsive. The general format for the electrical force is F, the force, magnitude of the force, is equal to K, which is Coulomb's constant, it's a constant, times the charge of the electron and the protons or the electrons acting on that electron, over r squared, where r is the distance between the charges. So Q, as Q2 increases, the force increases, it's a direct relationship. But because r is in the denominator and squared, it is going to have an exponentially reverse effect. So as r increases, F will decrease exponentially. Now, when we're talking about potential energy, remember that the lowest potential energy is the most stable potential energy. This is one of the laws of energy. As my force repulsive increases, so imagine two magnets that are being pushed together, the same poles are being pushed together, the force repulsive increases, and so the potential energy will increase. But if I have two magnets that have opposite poles that are attracted to one another, the closer I get to them, or the more force I have attracting them, the lower the potential energy. So part of what electrons want to do is they want to be as close to the nucleus as possible, in other words, increasing their force attractive as much as possible, and to decrease their force repulsive, so to be as far away from other electrons as possible. And where it ends up, its location is basically a sweet spot, that balance of maximizing force attractive and minimizing force repulsive. So part of what you have to remember is that we have a three-dimensional structure. Right? So I have my nucleus, and the electron, if it gets closer to the nucleus, force attractive goes up. Yay! But because this is a spherical shape, the closer it gets to the nucleus, the more crowded it gets with other electrons, so then force repulsive increases very quickly. So if I want to then go away, so farther away means that my force repulsive goes down because other electrons have more ability to spread out, but it's farther away from the nucleus, so the force attractive with the nucleus also goes down. So again, electrons try to be as close to the nucleus as possible, but maintaining that distance. So the more electrons that there are in an atom, the more it has to work hard in order for each of those electrons to attain its sweet spot so that it can be maximizing its what we call overall force of attraction on that electron. So this is what determines the address or the location, the most likely location of each of the electrons in an atom. So again, remembering that the nucleus and the area around the nucleus is a sphere, you can see that if I've taken a pie slice of this, that as I go away from the nucleus, there is more space. Right? So it's like there's a speaker at the center, not many people can fit around the speaker, but the farther away you go, more people can fit. So if I'm looking at this where this is nucleus and I've taken a little pie crust away from it, I can fit more electrons the farther away. If I'm very close to the nucleus, I can only fit 2 electrons closest to the nucleus, but the farther away I go, the more electrons I can fit in. So the farther away I am from the nucleus, the PE will actually increase because force attractive decreases. But I also will see a decrease in potential energy because my force repulsive will decrease because there's more space for the electrons. So what starts to happen is that these two factors, wanting to be closer to the nucleus but not wanting to have enough space, really determines the number of electrons that can be a certain distance away from the nucleus, kind of like auditorium seats. So force repulsive increases as electron density increases. The first and last electron in any given energy level, which is a physical distance away from the nucleus, is the same. So their physical distance is the same. But the first electron in any given energy level will have a low potential energy, where the last electron will have a much higher potential energy because it's now starting to come into a more crowded situation. So an analogy would be when you're, again, in a theater, the first person to sit down in a row has the most room to spread out. They can choose wherever they go. Chances are they'll sit on the aisle. Whereas the last person, there's a lot of tension, potential energy, because they have to squeeze in and ask all the patrons to go, excuse me, excuse me, excuse me, as they make their way into their innermost seat. And it's the same way with electrons as well. Everybody wants to have their space. The last electron that comes in is really making everybody feel a little bit uncomfortable. So distance-wise, electrons are going to be found the same distance away from the nucleus. So distance-wise, they're about equal distances from the nucleus. But PE-wise, it's going to be different. For example, in this second energy level, even though 8 electrons can fit in, the first 2 electrons will exist at a lower potential energy than the next 6 electrons. Similarly, with the 18 electrons in the third energy level, the first 2 electrons will be at a lower energy than the next 6, which will be at a much lower energy than even the next 10. In fact, the first 2 electrons in this fourth energy level actually have a slightly lower potential energy than these 10 electrons in here. Kind of like going back one row in a movie theater is a little easier than having to squeeze into the middle parts of that third row close to the movie screen. So if you're thinking about this as a movie screen, these are the distances of the rows of seats, and this is how much potential energy it takes in order to fill those rows up. So the potential energy of these electrons is not equal, and it has a very different feel than the actual distance. So the distances are the fixed, but the potential energy within a distance is not going to be fixed. So to reduce F repulsive between electrons, one of the things that electrons can do that we can't do is that they can spin. So electrons literally are spinning like they're whirling dervishes. And remember that when an electron spins, it creates a magnetic field. So if I have 2 electrons that are spinning, and one is spinning in one direction and the other is spinning in the opposite direction, they also create opposite electric fields. So even though electrically they're repelling one another, magnetically they are attracting one another, and so cumulative F repulsive decreases. But this only works with 2 electrons, right? So if you get another electron in there, there's no way that it can spin that would be opposite to both of the electrons that are already there. So there's a maximum of 2 electrons that are in a certain energy level in a certain type. So we call these orbitals. So orbitals sound like orbit, but they aren't. It's a region where electrons are most likely to be found. So the analogy I give is, if we're talking about my Whitfield density, the Emoto-Whitfield density at chemistry class time is most likely found in room 214. So you could describe the shape of room 214. And in fact, if we're having a lab, you could describe what my shape of pattern would most likely be between all the desks so I can circulate among you easily. I'm not as likely to be found in the parking lot, and I'm very unlikely to be found in H-Mart at that time. I may want to be, but I'm not going to be there. So the region where you're most likely to find me, if they want to find me, is going to be in room 214, but you can't predict exactly where I'm going to be at any given moment. It's the same type of thing with orbitals. With the electrons, because I know that the electrons are trying to balance maximizing force attractive, minimizing force repulsive, that there is regions of space around the nucleus and shapes of what those things are going to look like that are where the electrons are more likely to be found. And these are called orbitals, and they actually have certain shapes and orientations. So there are 4 different orbital shapes. There are S, P, D, and F. Every energy level has an S-type orbital. It's the simplest orbital. There's only one of them, and it has the shape of a sphere. If you have p orbitals, then you will have 3 of them located in the x, the y, and the z axes. That's why there's 3 of them. And they're peanut-shaped. They have a slightly higher potential energy than the s orbitals. And then the d orbitals, if there's enough room for d orbitals, are really weirdly shaped. Sometimes they look like 4 blotches. Sometimes they look like a sphere. You can look at them in your textbook to see them. There are 5 of those if there are d orbitals. And they have a higher potential energy than even the p orbitals. And then finally, if you are far enough and you have enough space, that energy level will have f orbitals. And there are 7 of those. Those are even more weirdly shaped. And they have the highest potential energy. Beyond that, the electron density becomes so large that the potential energy is too high for it to pack more electrons. That's why you'll notice in the previous slide there was a maximum of 32 electrons in any energy level, and that has to do with just the electron density. And the fact that in order to pack more electrons in, the orbitals have to be increasingly more complex in their shape. And for those of you who are interested, these orbital shapes are predicted by mathematics. There are things like what sine squared would look like, or cosine squared, because electrons move in wave-like functions. And it can get as complicated as cosine squared minus sine squared over cosine, things like that, that will give you these predicted shapes. So again, they go S, P, D, and F, and this just has to happen to be the lines that we see that are sharp, not so sharp, diffuse, and fuzzy. Precise, I think, is what P is. And that will make sense when we start talking about the Bohr series and the bright line spectrum.